Hi, everyone. Good morning, good afternoon, good evening, wherever you're joining us from. Here we are again with another session with Alex Devassy. Now, AI is talk of the town, and here we're going to be talking about the dark side of AI. So, without further ado, let me bring in Alex Devassy and we can get started with the session. Hi, Alex. Welcome to OWASP AppSec Days 2024.
Thank you. Thanks, ma'am.
The stage is all yours. Let's get started.
Yeah, sure. Hi everyone, myself is Alex, and today we're going to discuss about the dark side of AI, exploring adversarial threats. So before we dive into the technical stuff, let me give a brief intro on myself. So I am working as a security engineer in AppUX India. I am the project lead of OWASP LLM. So if you are into SAP pen testing, SAP systems review, or anything as such, you can definitely check out SAP. It's open source and it's hosted in OWASP. And it's a basically a graphical user interface where you can select modules and do enumeration and exploitation on SAP systems. And I'm also the author of Machine Learning CTF Challenges GitHub repo. You can either scan the QR code over there, or you can go into the link mentioned there, and you can see this repo where I have hosted practical AI applications where you can exploit and learn stuff. Like for all the CTFs there, the detailed solution is available as well in the repo. So yeah, if you're interested in that space, do check it out. And we will actually see some demos throughout this session, and the demos are hosted in this repo as well. And that's my LinkedIn profile over there. Like if you ever want to get in touch with me, that's the place you will find me. And yeah, moving on to the slides. So what we're going to discuss today is adversarial machine learning. And the adversarial machine learning is basically a study that focuses on attacks and defense against machine learning models. So what you see on the right hand side of the screen is that a definition given for adversarial machine learning from NIST and Meteor. But our focus on today will be like on purely on adversarial attacks. We will not be going into adversarial defensive strategies or techniques. Rather, we'll be focusing on completely on with an offensive mindset. We'll be discussing attacks like fast gradient sign method, FGSM. We'll be discussing attacks like inversion attacks and etc. So, yeah. So before we go and discuss on the attacks, it's important to know about the popular AI application architecture that's common now. So the architecture diagram you are seeing on the screen right now, it's an architecture diagram for RAG application, retrieval augmented generation. So before going into the diagram, we need to understand why we need RAG or retrieval augmented generation. So think about a use case where you have some of your personal documents, or you have your company's internal private documents, and the documents can be like 200 documents or something, and you want an LLM application which can query upon these documents. So what are the options you have? Like you can upload these documents into one of the publicly available AI cloud services or something like that, and you can query upon them. But that compromises the sensitive nature of these documents, right? So in this case, you need an LLM which can work internally within your network, within your boundaries, so that your sensitive data doesn't go out to the internet. So how can you build that LLM? If you go and build that LLM from scratch, or that machine learning model from the scratch, that will be a very cost intensive approach, right? Like you need huge amounts of data to train that. You actually need to do the training, and you have to go through all those processes in order to achieve your model. But with RAG, we can avoid that. So what we do in RAG is you take an open source model or a paid model. You take that model, you make that model work on your internal data. So how RAG achieves that is like that's where this architecture diagram comes in place. So in order to understand this architecture diagram, like we can take it up by bits by bits. So on the left hand side, on the left bottom corner, you can see one square. So that's the most important part in the RAG, I would say, because here you are taking your internal documents, like over here, you are taking your internal documents, you are feeding that into an embedding model. So what this embedding model does is it will generate embedding. So embeddings are nothing but vectors. So it will generate these vectors and store in a vector DB. So we have a vector DB. Currently, we have a vector DB which has all your documents in the vector form. So so we have that in the left hand side. On the right hand side you have your trained model, it can be an open source model like Mistral, or like a paid model from OpenAI, or whatever it is. So you have that over here, or you can actually train your own model, like if you have that sufficient training data. So that's the piece you see over here. And the this component over the top, it's the orchestration layer. It's where you host your application, and you implement frameworks like LangChain or Llama Index, that sort of thing. So when a user inputs the prompt or the user request through the API endpoints, that prompt will come to the orchestration layer, where that prompt will be given to an embedding model. This can be the same embedding model as over here as well. So it will be the same embedding model. That embedding model will generate the embeddings or vectors with respect to that user input. Then with those vectors, what next happens is the application will do a similarity search on this vector DB, so that it will get the data which is similar with respect to the user prompt. This will be the context to our AI application. So instead of this will be the context to our AI application. So this context will be given to the system prompt. So system prompt is again in the orchestration layer. So you can think system prompt like this. So if you are building a financial assistant, you can mention in the system prompts such a way that behave like a financial assistant, and use the context from the vector DB. So that will be defined in the system prompt, and the context will be given from the vector DB with respect to the user input. And this system prompt as a whole will go to the LLM model, or the trained model, or the custom model, so that the output generated by the LLM will be very specific with respect to your personal data or your internal data, rather than if you are querying on the uh, paid models out there, like for example GPT, it will give you like a response in a very generic way, right? But this with this RAG architecture, you can get a response from LLM which is very specific to your data. That's the benefit of using an RAG architecture. So what I've done here is I have plotted out various attacks that can happen at various stages in this RAG architecture. For example, if you are if you are going to train a model by yourself, then the training data will be a crucial part of your application, right? So if that training data itself is poisoned through training data poisoning, then your model will not behave in the correct way. So training data poison happens over here. Then we have model poisoning, like if it's more like an internal threat if you are developing your own model. So model poisoning can happen in that place, or if you are like downloading an open source model from an untrusted source or something, the models can be itself from attackers, and it will be a malicious model. So those attacks happen over here. In the API endpoints which are queried from the user, there can be attacks like prompt injection, model inference, model evasion, etc. So what we're gonna do in the rest of the slides are like we're gonna discuss each of these attack vectors. We're gonna see some demos, and we're gonna see them in the detail. So that's what we're gonna do. And moving on to the next slide, we have supply chain attacks. So supply chain attacks is not something which is not familiar to a security person, right? It's not specific to AI. It's more of a generic attack. So what I've done included in this slide is a case study for one of the famous supply chain attacks that happened in OpenAI, specifically in ChatGPT. So what happened here was GPT was using a vulnerable version of Redis spy library, and the attack basically goes like this. So for each user input that comes into GPT, what GPT does was in its backend, it was taking a connection from a connection pool and using that connection to process the user request and render the response back to the user. The problem happened where the server decides to close this server decides to terminate a user request in its midway, so that the connection will be taken from the connection pool. The user request will be processing in the backend, but the server decides to terminate that request, and the connection pool and that but the connection that used for processing that request is retrieved back into the connection pool without terminating the data. So when a next user comes in and give the user request, the same connection will be taken in the connection pool with the leftover data and rendered the response back to the user. So that particular user can see the leftover data of another users and everything. So it had a pretty big impact to GPT. Like it revealed payment related information and all sorts of such sensitive information. So you can go into this link where they have a pretty good technical postmortem on this particular issue, and you can see more details on it. The reason why I included this slide in this discussion was that I want to communicate like we need to treat AI application like any other application. Like do, it should not be different due to the fact that we are incorporating AI. We should ensure that all the security controls we implement for an generic application or a traditional web application should go for an AI application as well, because of the threats are applicable here. So yeah, that's supply chain attacks. Moving on, we have training data poisoning. So training data poisoning is something very specific to AI applications, I would say. As the name implies, it's like a poisoning of the training data set. So like I said, if you're going to train a model from scratch, the first thing you need is data. Like you need huge data, a huge amount of data. So you can go into sources like Kaggle, Hugging Face, or any other source to get this data. The issue arises when the source you go and get this data is not a trusted source. So if you are like getting the data from, for example, if you're getting the data from dark web or something, you never know if that data is like poisoned or not. So we'll have a demo for this. So before going to the demo, I'll explain the code which I used in the demo. So the code you see on the right hand side, like if you are developing machine learning applications or like coding ML stuff, you would know this code is very simple code. So what I've done is I have used Keras over here, and I have used a specific data set from Keras, which is MNIST. So MNIST is a data set of handwritten numbers. So what MNIST consists of is like images of handwritten numbers from 0 to 9. For example, it will have an image of 0 and a corresponding label, like this image which says this image is 0. For image of 1, it will have a corresponding label like this is image of 1. Likewise, it's a small data set. So what I'm doing here is that poisoning happens in this for loop. So what I'm doing here is I am for all images of the number 2, I am modifying the label as 9. So when you train a model with this data, the model will interpret all images of 2 as 9. That's it. It's a simple training data poisoning. So for the demo of this, let me go over here, refresh this again. Yeah, let me refresh this so that the demo is here. Yeah, so this is from my GitHub repo, and this is the demo. So the demo is like the scenario for the demo is that you are part of an heist crew, like you are part of the heist crew and you are in the heist crew car, and you need, after the heist, you need to bypass the AI cameras. So that's the scenario here. So here you are doing the heist, and here you will be getting busted because of the AI cameras detected your licensing plate. So if you look closely into the license numbers over here, the high screw car alone, this is the license plate number for high screw car, and you can see this number is having the number 2 in it. None of the other license plate is having the number 2. So this is the first clue to solve this, and the rest of the things are like regular CTF only. You need to have you need to get access to the admin panel, you need to upload your malicious training data set, you need to train the model. So on the left hand side you can see the training taking place. So when you upload the malicious training data set, remember, for all the images of 2 we have swapped the label as 9. So yeah, so the training is complete. Now I click on simulate. Now when the model sees the high screw car number plate, and when it sees the number 2, it will interpret as 9. So you'll get bypassed at the AI camera detection. So yeah, this is a one POC demo for training data poisoning. Going on, we'll go into model serialization attacks. So uh, this is an interesting case, I would say. So deserialization attack is nothing. It's not something that is familiar to a security person, right? It is always been there. So here we see how we can do a deserialization attack with respect to machine learning models. So the risk of these attacks comes when you decide to download an open source model, or there are multiple sources to do that, right? For example, Hugging Face is one source, Olam is one source, and the issue comes when you download a model from an untrusted site again. So you never know what's inside the model, right? It's like downloading an exe. You never know what's inside the exe, correct? So it's the same thing happening over here. So in those particular case, there is a good open source tool, model scan. So you can use model scan to scan the downloaded models, so that you can know if there is any malicious code in it or not. So the code you see on the right hand side of the screen over here, it's a code for generating a malicious model. So yeah, I just told like models, you can use model scan for scanning your model and all, but models can also provide libraries for generating malicious model. So I am using pickle inject library from model scan, and what I'm doing is I am injecting a Python reverse shell into the model. So and I'm generating the model over here. You can see the generated model over here. It's unsafe model underscore pyshell.pt. It's a PyTorch model. I'll show this in demo, so it's much clearer on that. Again, this demo is in my GitHub repo, like you can go and see it. So in this demo, what I'm doing is I'm hosting an application. Yeah, so it's an application where you can select the models and input text. So when you give the text and click on analyze, the backend model will show the sentiment analysis of that particular text. So in this case, it's the sentiment analysis score is 80%. So that's what this application does, and this application also supports like uploading of custom models. So I showed you the code for creating malicious models, right? So I am uploading that malicious model here right now. Before uploading, I'm creating a reverse shell. I'm creating a listener and I'm uploading the model, and you can see that the model is successfully uploaded, but we are not having the reverse shell yet. I'll tell you the reason for this. So here we are executing a statement on top of that model, and only when that model is loaded by the application, then only we'll get the reverse shell. So we have the reverse shell over here, and we can execute OS commands and all those sort of things. Yes, because it's a CTF, you can get the flag. The interesting thing happens after this. So here, even though it's giving you a reverse shell, the model works as intended. It's still giving out an accurate sentiment analysis of that particular statement you have inputted. So yeah, so this is an example for model serialization attacks. Moving on, we have inversion attacks. So uh, yeah, inversion attacks is my personal favorite, because in what you do in inversion attacks is like you query the model endpoints, like it can be API endpoints, or you can directly query the model, and you try to extract the training data set. So the image you see on the left hand side of the screen is taken from a paper called Modern Inversion Attacks that exploit confidence information and basic countermeasures. So what these guys are doing is they are extracting the training data set. In this particular case, it's AT&T faces. They are extracting it because yeah, they are extracting this faces from the trained model. So yeah, imagine the impact this could have this could have on a model used for facial recognition. So that's what they are doing on the left hand side. On the right hand side, it's a much simpler POC from art adversarial robustness toolbox. It's a public GitHub repo out there. So what these guys are doing, they are extracting the training data. In this particular case, the training data is MNIST data set. Like in the previous slides, we went through the MNIST dataset, right? It's a dataset of handwritten images, like from 0 to 9. So we can see that extraction over here. And yeah, so what we'll be looking in detail is on this one. We have a demo on that. But before going to the demo, I'll show the POC code for this. So the code you see on the right hand side is the POC code for doing a model inversion attack. Again, it's a simple code only. So before going into this code, I would like to mention one thing. So I have used, I have initialized multiple variables here. For example, image y size, image x size, classes, etc. So if you ask me how I get these values for these variables, so that involves a bit of reverse engineering of the model. So that the screenshots you see on the left hand side, I have used a tool called HDF view to reverse engineer the model. So what I'm doing here is I'm uploading the model. Oops, sorry. So what I'm doing here is I'm uploading the model to HDF view, and the tool is like showing me various parameters inside the model, the architecture of the model, and etc. So from this, by doing this reverse engineering, I'm able to get these values. So that's something important to note. Not only these values, like for example, the loss object to use. All this information are coming from this reverse engineering step. So I have declared all these things like loss object. This is nothing but the input shape. Parameter. This is nothing but the input shape. Yeah, and you can ignore this inversion function for now. I'll explain that. Coming to the next piece of the code or next line of the code, I'm just declaring a black image. So to start with, that's it. And classes are nothing but labels. So in this case, we have classes as 4, right? So it means that if you give an input to this model, it will classify that input to any of these 4 labels. That's it. So that's the classes. And for each classes, I am doing an iteration with this black image being starting with this black image, and I'm calling this inversion function. So in order to understand this inversion function, which is the core of this attack, we need to know the concepts like gradient descent, loss function, and everything. Sorry, but it would be really hard for me to go through those things in a short time span. But what I'll try to do is I'll try to explain those things with the help of a graph. So the graph you see over here is a simplified graph for explaining gradient descent, basically. So if you ever wonder how machine learning models arrive in a prediction, like they use optimization algorithms, and gradient descent is one of such optimization algorithms. The concept here is like a machine learning model, the accuracy for the machine learning prediction model's prediction will increase as you go down over here, and the best accuracy will be achieved in the local minima. So how does the model know like how to reach the local minima? So in order to reach the local minima, the machine learning model use something called loss function. So the lower the loss function, the accuracy will be high, and the accuracy will be best in the local minima. If you are going beyond the local minima here, the accuracy will be like lesser and lesser. So that's what it is. Yeah, for now you can think of it like this. Like gradient descent is an optimization algorithm used by machine learning and machine learning models. And yeah, so what we are doing in this inversion function is at a high level we are like decreasing the loss function so that we are increasing the accuracy. That's what going on at a high level over here. uh, I'll give you a demo on this. Let me refresh the page so that the video gets loaded properly. Yeah, so this is the Vault machine learning CTF I have in my repo. So yeah, you can download the model as part of the CTF. You can see the model over here. But if you go into the application, what Vault does is it requires 4 persons face to get access into the vault. So that's the scenario over here. So if you are selecting random faces and clicking on submit button, it will give you an access denied. So it basically mimics facial recognition application. That's it. So now it's time to work on reverse engineer that downloaded model and extract the training data set. So the code I'm executing here is the same code which I've shown in the graph. I'm shown in the slide. So you can see the results of the training data extraction over here. The next thing we have to do is we have to select the corresponding images from this image list, and you will get access into the vault. So yeah, for the detailed solution like explanation of code and everything, you can go into this repo, check out the solution page. It will have the very detailed explanation for this. Yep. Moving on, we have evasion attacks. So if you are ever been trying to learn adversarial machine learning or anything such, I'm quite sure you would have seen this image of the panda. The reason being, it's a very popular and it's a very interesting attack to attack in adversarial machine learning. So it's from the paper of Ian Goodfellow. I would suggest to read this paper if you are planning to start an adversarial machine learning space. We'll go through this image detailedly and work you, and see what's happening. So the image you see on the right hand side, it's taken from the paper fooling automated surveillance cameras adversarial patches to attack person detection. So what these guys are doing over here is they are generating adversarial patches, so that when you attach this adversarial patch to in this case a person, the model that classifies the objects in this video or image misclassifies this person or fail to misclassify this person. You would have seen images like people posting these kind of adversarial patches on stop signs and everything. So in a world where autonomous cars are there, if you do this attack, it would be very catastrophic. Yeah, so we leave that adversarial patch over here and we'll focus on this image for now. So this image comes from a popular attack called fast gradient sign method, FGSM in short. So what happens in this image is, if we pass this image on the extreme left to a machine learning model, the machine learning model will correctly classify this image as a panda with a 57% confidence. But if you are embedding calculated distortions into this panda image and then feeding the adversarial image, which is on the extreme right side, into the machine learning model, it will misclassify it as gibbon. Uh, Even though for a human eye this is a panda, the machine learning model will misclassify it as a gibbon. So what we're gonna see is we're gonna see how we can generate these calculated distortions, and finally how we can generate this adversarial image. So that's what we are going to look in. So in order to generate this adversarial image, this is the formula, and this is the I would say very important formula for FGSM. So what we're gonna do is we're gonna look into this formula in detail. Yeah, so this is on the extreme left hand side we have adversarial image, and this axis the input image, the image you just saw, right, the image of the panda, and this is the place, the extreme right side is the place which is responsible for creating that calculated distortions, this part. So what we are doing is we are creating that calculated distortions and we are embedding that into the input image, so that we get the adversarial image. So uh, again, if in order to explain this formula completely, I need to go through concepts like the gradient descent and everything. But at a high level, what's happening over here is we are increasing the loss function such that the model will misclassify the input image. So compared to the previous attack we discussed, right, inversion attacks where we decrease the loss function so that the model's classifications become much accurate. Here we are increasing the loss function so that the model's predictions becomes less accurate. So that's what we are doing over here. And yeah, we have a demo for FGSM as well. So if you can try this out demo by yourself. You can scan this QR code and you will get a Google Colab where I have posted the complete code for this. So yeah, the code goes like this. I will go into the code in Colab so that it's much more easier. Yeah, so if you scan that QR code, this is the Colab you're gonna get. And the model we are trying out FGSM is MobileNet V2. We can see that over here. So at first we are giving it an image of Labrador Retriever dog. So the model classified correctly as a Labrador Retriever dog itself. The next thing we're gonna do is we're gonna generate the distorted image. So this is the distorted image, and we are embedding that into the input image, so that yeah, so that we get the adversarial image. And this is an example of adversarial image. So this adversarial image looks as like a Labrador Retriever to the human eye, but the model will model will misclassify it as something else. So as you increase the value of epsilon, the adversarial image becomes more and more suspicious, but the misclassification of the done by the model will increase. So yeah, so this is FGSM attack. You can try this out. Like I said, the Google Colab is publicly hosted. So yeah. So the next attack we're going to discuss is prompt injection attack. So by that this time I'm quite familiar, like I'm quite sure like almost all of you will be familiar with prompt injection attack. But we're gonna look prompt injection attack from a different perspective. So the screenshot I have posted over here, it's one of the screenshot, one of the Twitter post, one of the first Twitter post actually that sparked the discussion on prompt injection. So it's self-explanatory, right? It's nothing fancy going over here. But the issue with doing such prompt injection is that like it's not impactful to the application. So if you think it from a CIA perspective, like confidentiality, integrity, or availability perspective, there is no big impact from that perspective to the application, right? It's just it's a still prompt injection, but the impact is much less. So what we're gonna see is like how we can cause impactful prompt injection. So for that, we need to have an understanding on how AI applications work, what are the components that used in the backend by the AI architecture and all. So most probably the AI application you will be interacting will be a RAG application. Uh, I'm saying this because RAG is the most popular architecture as of now, but there are new architectures coming like architectures using AI agents and everything. So yeah, AI is a ever evolving, I mean rapidly evolving landscape. So that can happen. But as of now, RAG is the most popular one out there, and the most of the LLM applications you will be interacting will be most probably be RAG, because think of it like organizations that using RAG organizations doesn't have to like build model from scratch, doesn't have to go through the entire process of training data, getting test data, and all those things. Organizations can just simply use RAG with their internal documents or internal data uh, and integrate with an LLM model. Yeah. So if it's a RAG application, there will be definitely be orchestration happening in its backend, and LangChain is one of that orchestration frameworks. So, uh, I'll show how we can exploit this. The demo we're gonna see is with respect to LangChain, and with respect to specific chain in LangChain called program-aided language chain, or PAL chain in short. So I think it's better to go into the demo so that we can see this much clearer. Let me refresh the screen so that the video plays well. Yeah, so this is Dolo's City of Challenges in the same GitHub repo. So it's an LLM application, web-based application. So you can see I am capturing the traffic in WebSuite, right? It's the first thing we hackers do. So in that traffic, I can see that from the response headers and from the source code, inspecting the source code of the application, I can see that application is using a specific version of LangChain in backend. So what I'm attempting here is an payload for a particular CV in LangChain. So I'll attempt that payload. It's a OS code execution payload, but it's the application is saying possible injection detected. The reason for this is this application is in its backend, in this application's backend, there is something called a rebuff framework. It's a prompt injection detection framework, and if you implement rebuff, it can detect prompt injections. So, but even though the application is implemented a rebuff framework, it's not implemented in the proper way. Like you can bypass the rebuff framework using response tampering. It's not a vulnerability in rebuff, rather it's a bad configuration that developers took while they code this application. So I'm doing response tampering over here, and yeah, once I bypass the prompt injection detection, I can see the code is getting executed, and I can see the internal folders. So yeah, so this is an example for causing impactful prompt injection. Coming back to the slides. The next prompt injection attack is on Llama index. Llama index is something similar to LangChain. I would not say something similar. It's an entirely different framework, but it's used for orchestration. So in this demo, what we're gonna see is we're gonna see how we can exploit vulnerable version of Llama index, particularly the text to SQL feature of Llama index. So what happening here is Llama index is using text to SQL feature so that when users are inputting something, users are inputting their queries in natural language, Llama index can retrieve the corresponding data from the SQL database and render that to the users. So that's what is happening here, and you can see in the screenshot in Llama index official documentation, there itself they are saying it's a risky feature to use. We'll see how to explore this. So yeah, I have work screenshots over here. Again, this is hosted in the GitHub repo as $2 CTF. So if you want to try it out hands-on, you can try it out there. So here, what's happening is we are trying to execute an SQL command in the prompt, select star from employees table, but but the application is throwing us some errors, like it's detecting prompt injection over here, or it's detecting SQL queries. You can see this much clearer over here. When I use commands like show, it's detecting it as an SQL query. So what developers has done here is in the system prompt, they are defined or they have blacklisted particular SQL keywords, so that when there is that keyword in the user prompt, they are classifying it as malicious, and they are not the application logic is not going forward. So the attacker can, it's, which is a bad security thing to do. Like it's a very bad practice to implement security controls in the system prompt. There should be other mechanisms in place in order to prevent prompt injection or any sorts of that kind of things. So yeah, so the attacker can simply bypass this by using another keyword and another word exactly instead of show. So attacker is using list over here, and we can see we can retrieve successful data from the database, and we can get the flag as well by using the queries. So yeah, that's on Llama Index. Moving on, we have three specific uh, attacks which is listed in OWASP LLM top 10. We'll go one by one. So the first one is overreliance. So the name suggests, like if you overrely on the LLM, you're gonna have security incidents. Imagine a scenario where you use the code generated by LLM without doing any security review or anything such. That would end up in a bad situation. Insecure plugin is something interesting. So in insecure plugin, uh, with respect to the use case of the LLM applications, in the LLM architecture, there will be multiple components. Like for example, there will be a plugin which can go into the internet and parse a website or take the data from a website or something that sort of nature. So here, if those kind of plugins are insecure, then you can have security incidents. So the uh, thing which I highlighted in red over here is a payload for doing indirect prompt injection. So this is I took this from the blog of Embrace the Red. So here what they are doing is they are hosting a malicious website, and they are hosting an image in the malicious website, so that when an LLM application passes that website, the user's chat history will be given to the attacker's server. So that's what they are doing over here. And the final one, we have excessive agency. So excessive agency is like giving more privileges or more power to the LLM application. Imagine a scenario where you give power to an LLM application such that the LLM application can send out mails by itself. So in those kind of scenarios, this access agency is an issue. Like if you go and explore the security best practices from OpenAI itself, they are recommending to have human in loop so that access agency risk are mitigated. Yeah, I guess that's it. Thanks everyone. Thanks for your time.
Thank you so much, Alex. That was very wonderful. And a lot of things that you shared, especially I really like the prompt injection part, because I'm actually researching in this area and there's so much to learn.
Yeah.
Great. Thank you so much. And we have some people have questions, but they're going to reach out to you on your LinkedIn handle or Twitter handle, and stay tuned for it.
Sure, sure. Yep.
Thank you so
Thank
much,
you.
everyone. Do reach out to Alex and have a great day. Also, stay tuned for the upcoming sessions.